How big is the Andromeda Galaxy? Really, you are looking at an entire galaxy of 1 trillion stars, and the light entering your eyes right now began its journey before humans existed. Let me say that again, because it's worth sitting with. The photons landing on your retina left Andromeda when our ancestors were barely recognizable as human. 2.5 million years ago, while these particles of light were crossing the void between galaxies, early hominids were just learning to craft the first stone tools on the African savanna. Entire species have evolved and gone extinct during this light's journey to you. The light is older than our species, older than our genus, older than most of the story we tell about what it means to be human. And yet, despite this almost incomprehensible distance, Andromeda is our neighbour. It's the closest large galaxy to our own Milky Way. In cosmic terms, Andromeda is practically in our backyard, rushing toward us at over 250,000 miles per hour for an appointment our galaxy will keep in about 4 billion years. When these two island universes collide and merge, they will create something entirely new, a supergalaxy that future astronomers have already nicknamed Milkomeda. But tonight, we're going to do something extraordinary. We're going to understand just how big Andromeda really is, not just in numbers that slide off our minds like water off glass, but in ways that connect to our human experience and fundamentally change how you see the night sky forever. Here's the challenge we face together. The human brain didn't evolve to understand galaxies. We evolved to estimate the distance to the next tree, to judge whether we could outrun a predator, to recognize a familiar face across a clearing. Our intuitive grasp of scale maxes out at a few miles, maybe the view from a mountaintop on an exceptionally clear day. Galaxies exist on a scale so far beyond our evolutionary hardware that saying Andromeda is 220,000 light-years across means almost nothing to our actual comprehension. The words are English, the numbers seem straightforward, but the meaning evaporates before it can truly land. So here's what we're going to do over the next 3 hours. We're going to build a ladder of understanding, rung by rung, that will carry you from everyday human scales up to the genuinely cosmic. We'll start with things you can touch and see, then carefully, systematically stretch your mind across distances that would make infinity feel jealous. We're going to use every mental tool available to truly grasp what it means when we say Andromeda contains 1 trillion stars, that it spans distances light itself takes hundreds of thousands of years to cross, that its gravitational influence extends so far that it's already pulling on our own galaxy like an invisible rope connecting 2 boats on an ocean. By the time we're finished, you won't just know how big Andromeda is in an abstract sense. You'll have internalized it, felt it in your bones, built a working model in your mind that you can turn over and examine from different angles. You'll understand why astronomers sometimes just stop in the middle of their work and stare at the sky in amazement. You'll know why Carl Sagan's voice trembled slightly when he talked about the cosmos. You'll grasp why the simple act of looking up at that fuzzy patch of light should fill any thinking person with a profound sense of wonder and cosmic humility. This is going to be a journey, and I won't lie to you, It's going to stretch your imagination in ways that might feel uncomfortable at first. Our brains will resist. They'll try to shrink these distances back down to something manageable, something that fits in the box marked things I can understand. But I promise you, if you stay with me, if you let yourself sit with the discomfort of truly enormous scales, something remarkable will happen. The universe will get bigger, yes, but paradoxically, you'll also understand it better than you ever have before. So take a deep breath. Maybe make yourself comfortable with something warm to drink. We're about to embark on one of the most mind-expanding journeys available to human consciousness. One that requires no spacecraft, no advanced degree, just a willingness to look up at the sky and ask that most human of questions. How big is that really? Let's begin where all good understanding begins, with the familiar, and work our way outward to the edge of comprehension itself. Part 1. Building the foundation. Understanding distance and scale. The problem with numbers. Before we can understand Andromeda's true size, we need to confront an uncomfortable truth about how our minds work. When I tell you that Andromeda is 2.5 million light-years away, your brain processes those words, but it doesn't truly comprehend them. This isn't a failure of intelligence. It's a fundamental limitation of human cognition that we all share. Consider this experiment. I can tell you that 1 million is 1,000 times larger than 1,000, and you understand that intellectually. You could do the math, verify it's correct. But do you really feel the difference? Let me make it concrete. If I gave you $1 per second, you'd have $1,000 in about 16 minutes. You could wait that out, maybe watch a TV show. But to get to $1 million at the same rate, you'd have to stand there collecting $1 every second for 11.5 days, without sleeping, without stopping. That's the difference between 1,000 and 1,000,000, and we throw around million so casually that we've lost touch with its true magnitude. Now, Andromeda isn't millions of anything simple like dollars or seconds. It's millions of light years, and a light year is already so large that it defies everyday understanding. Light travels at 186,282 miles per second, or if you prefer, about 670 million miles per hour. This is nature's speed limit, the fastest anything in the universe can move. In a single year, light covers approximately 5.88 trillion miles. That's the unit we're using to measure Andromeda. And we're saying it's 2.5 million of these units away. The numbers become abstract so quickly that they lose meaning, which is precisely why we need to build our understanding more carefully, starting from a scale our minds can actually grasp. The Earth. Our starting point. Let's begin with Earth, the only planet we truly know from direct human experience. Our world has a diameter of about 7,900 miles at the equator. If you drove non-stop at highway speed, it would take you roughly a week to drive a distance equal to Earth's diameter. That's comprehensible. You've driven for hours before, you can imagine doing it for days, and a week is a time span you've experienced many times. The Earth orbits the Sun at an average distance of 93 million miles, a distance we call 1 astronomical unit, or AU. This is our first really big number, but we can make it feel more real. If you could build a highway from Earth to the Sun and drive it at 60 miles per hour without stopping, it would take you about 177 years to arrive. That's roughly 2 human lifetimes, which means if your great-great-great-grandfather had started driving when he was born, and each generation continued the journey in an unbroken relay race across centuries, you might just be arriving at the Sun's surface now. Already we're dealing with distances that dwarf human experience, but we're still within our solar system, still in what we might call our cosmic neighborhood. The solar system, our local environment. Our Sun's empire extends far beyond Earth's orbit. Neptune, the outermost major planet, orbits at a distance of about 30 astronomical units, or roughly 2.8 billion miles from the Sun. But even Neptune doesn't mark the true edge of the Sun's gravitational dominion. Beyond the planets lies the Oort cloud, a vast spherical shell of icy bodies that surrounds our solar system like a cosmic bubble. The Oort cloud extends to distances of about 100,000 astronomical units, or roughly 1.6 light-years from the Sun. This is where our solar system truly ends, where the Sun's gravity finally weakens to the point that other stars begin to exert comparable influence. Think about that for a moment. The Sun's gravitational reach extends nearly 2 light-years out, meaning light from the Sun would take almost 2 years to reach the outer edge of its own solar system. If someone turned off the Sun right now, like flipping a light switch, the outer Oort cloud would remain illuminated for nearly 2 more years before finally falling dark. The journey to Proxima Centauri, our nearest neighbour. The nearest star to our Sun is Proxima Centauri, part of the Alpha Centauri system, sitting at a distance of about 4.24 light-years. This is our very closest stellar neighbour, and yet the distance is so vast that it challenges every intuitive sense of scale we have. Let's try to understand this distance through comparison. Remember that highway to the Sun that would take 177 years to drive? A highway to Proxima Centauri at the same speed would take about 8 million years. That's longer than our species has existed. Homo sapiens emerged roughly 300,000 years ago, which means you'd need to make the journey to Proxima Centauri about 27 times to equal the entire span of human existence. Our fastest spacecraft, Voyager 1, is currently traveling away from the Sun at about 38,000 miles per hour relative to our star. This probe, launched in 1977, has traveled farther from Earth than any other human-made object. At its current speed, if it were headed toward Proxima Centauri instead of its actual trajectory, it would arrive in about 73,000 years. Imagine that. We'd need to wait longer than all of recorded human history, plus another 68,000 years or so for our fastest spacecraft to reach our very closest stellar neighbour. This is the fundamental challenge of interstellar travel, and we're only talking about the distance to one nearby star. Andromeda contains 1 trillion such stars spread across a volume of space so enormous that our journey to understand it has barely begun. The Milky Way, our home galaxy. Now we begin to approach truly galactic scales. Our home galaxy, the Milky Way, is a barred spiral galaxy containing somewhere between 200 and 400 billion stars. It measures approximately 100,000 to 180,000 light-years in diameter, with our Sun situated about 27,000 light-years from the galactic center. Let me help you feel that distance. Remember Proxima Centauri at 424 light-years? The center of our galaxy is about 6,400 times farther away than our nearest star. If we built that highway again and drove toward the galactic core at 60 miles per hour, we'd be driving for 485 million years. That's longer than complex animals have existed on Earth. That's before dinosaurs, before the first fish crawled onto land, before plants covered the continents in green. Our Sun orbits the center of the Milky Way at a speed of about 514,000 miles per hour, and yet it still takes approximately 225 million years to complete one orbit. This is called a galactic year or cosmic year. The last time our Sun was in its current position relative to the galaxy, dinosaurs hadn't yet evolved. Earth was in the Triassic period, and the Atlantic Ocean didn't exist yet. Now, here's where it gets truly mind-bending. There are hundreds of billions of stars in our galaxy, each one potentially with its own family of planets. Some of these stars are clustered relatively close together in dense stellar neighborhoods. Others drift in the vast spaces between spiral arms, lonely wanderers in the cosmic dark. The galaxy isn't uniformly populated. It has structure, architecture on a scale so grand that light itself takes hundreds of thousands of years to trace its outline. Think about the implications of this. Right now, at this very moment, there is light leaving stars on the far side of our galaxy that won't reach Earth for 100,000 years. That light will arrive on a planet that might be utterly transformed from the one we know today. Our civilization might be gone, evolved into something unrecognizable, or scattered to other stars. The light doesn't care. It just keeps traveling at its constant speed, carrying information about a star that might not even exist anymore by the time anyone receives the message. The scale we've built so far. Let's pause and review the ladder we've climbed. We started with Earth, about 8,000 miles across. We stretched to the Sun, 93 million miles away. We reached out to Neptune, about 2.8 billion miles distant. We touched the edge of our solar system at the Oort cloud, nearly 2 light-years out. We made the leap to Proxima Centauri, our nearest star, at 424 light-years. And finally, we grasped the span of our own Milky Way galaxy, measuring up to 180,000 light-years from edge to edge. Each step was a leap in scale of hundreds or thousands of times the previous step. Each transition required us to let go of our intuitive sense of distance and build new mental models. And yet, with all of this work, with all this stretching of imagination, we still haven't left our own galaxy. Andromeda exists in an entirely different order of magnitude, separated from us by a gulf of space that makes the span of the Milky Way look almost trivial. We're ready now to make the final leap, to cross the intergalactic void and come face to face with Andromeda itself. But first, we need to understand what we're looking at when we talk about a galaxy at all. Part 2. What is a galaxy really? Islands in the void. Before we can appreciate Andromeda's size, We need to understand what a galaxy actually is, beyond the simple definition of a large collection of stars. Galaxies are not just random groupings of suns scattered through space. They are coherent structures, bound together by gravity, with their own internal dynamics, their own life cycles, their own evolution across cosmic time. Imagine you're floating in the darkest place in the universe, somewhere in the vast emptiness between galaxy clusters. You're so far from any star that the darkness is absolute, deeper than any darkness achievable on Earth. Your eyes, fully dark-adapted, scan the black, and then you see them, faint at first, but growing clearer as your vision adjusts. Scattered through the void, like islands in an infinite ocean, you see galaxies. Hundreds of them, thousands of them, each one a complete universe of stars unto itself. This is the fundamental structure of our cosmos. Galaxies are the building blocks of the observable universe, the primary organizing structures of matter on the largest scales. Just as atoms combine to form molecules, and molecules combine to form cells, and cells combine to form organisms, stars combine to form galaxies, and galaxies themselves cluster together in even larger structures called galaxy groups and galaxy clusters. The architecture of a spiral galaxy, Andromeda, is a spiral galaxy, much like our own Milky Way, which means it has a particular architecture that we need to understand. At the center sits a dense bulge of older yellowish stars, packed together far more tightly than stars in the spiral arms. This central bulge harbors a supermassive black hole with a mass of about 100 to 200 million times that of our Sun. Don't let the term supermassive mislead you into thinking this black hole is large in physical size. The event horizon, the point of no return, is only about 1 billion miles across. That's roughly the distance from the Sun to Jupiter. This means an object containing as much mass as 100 million suns is compressed into a region that would fit comfortably in our inner solar system. Extending outward from the central bulge are the spiral arms, magnificent sweeping structures traced out in the blue-white light of young, hot stars and the pink glow of hydrogen gas where new stars are being born. These arms aren't solid structures like the arms of a pinwheel. Instead, they're density waves, regions where stars and gas are temporarily compressed as they orbit the galactic center at different speeds. Think of them like traffic jams on a cosmic highway. The cars in a traffic jam are constantly changing, flowing through the congested region, but the jam itself persists in the same location. The stars in a spiral galaxy don't all orbit at the same speed. Stars closer to the center orbit faster, while stars farther out orbit more slowly. This differential rotation should, theoretically, wind the spiral arms up tighter and tighter until they disappear, like winding up a clock spring. The fact that spiral arms persist means something is continuously refreshing them, and that something is the density wave, a pattern that rotates at its own speed, independent of the individual stars. Between the bright spiral arms lie regions that appear darker, but they're not empty. They're filled with stars too, just older, dimmer stars that don't stand out against the brilliant young blue giants in the arms. And permeating everything visible and invisible, is the dark matter halo. The dark matter mysteries. Mystery. Here we encounter one of the most profound mysteries in modern astronomy. When astronomers measure how fast stars orbit in galaxies, they find something unexpected. Stars far from the galactic center orbit much faster than they should based on the visible matter we can see. The orbital speed should drop off with distance, just like planets in our solar system orbit more slowly the farther they are from the Sun. But in galaxies, the orbital speed stays roughly constant even at great distances from the center. There are only two possible explanations for this observation. Either our understanding of gravity is fundamentally wrong, or there's additional matter present that we can't see, matter that doesn't emit, absorb, or reflect light of any kind. This invisible substance, whatever it is, has been named dark matter. Based on orbital speeds and gravitational lensing observations, astronomers estimate that dark matter makes up about 85% of all the matter in galaxies. Let that sink in. Everything we can see, all the stars and gas and dust, all the planets and asteroids and comets, everything that emits or reflects light in any way, constitutes only 15% of the total matter. The rest is invisible, interacting with normal matter only through gravity. Andromeda, like all large galaxies, sits at the center of a massive dark matter halo that extends far beyond the visible stars. This halo is roughly spherical and may extend several times farther out than the visible galactic disk. The total mass of Andromeda, including all this dark matter, is estimated at about 1.5 trillion times the mass of our Sun. The visible stars account for only a fraction of this total. What this means is that when we measure Andromeda's size, we're really talking about two different things. There's the visible galaxy, the part we can photograph and map with telescopes, extending about 220,000 light-years across. And then there's the complete gravitational structure, including the dark matter halo, which may extend 3 or 4 times farther, making the total gravitational influence of Andromeda span perhaps 800,000 light-years or more. The stellar population. Within Andromeda's visible structure shine approximately 1 trillion stars. Let's try to comprehend this number. A trillion is a million millions, 1,000 billions. If you counted 1 star per second without stopping, it would take you about 31,700 years to count them all. That's longer than the entire span of human civilization from the earliest agricultural settlements to today. But simply knowing the number doesn't convey the diversity. Andromeda contains every type of star we know exists. There are red dwarfs, small cool stars that burn their fuel so slowly they might outlive the universe itself. There are stars like our Sun, medium-sized yellow stars in the prime of their lives. There are red giants, bloated stars in their old age, having swollen to hundreds of times their original size. There are blue giants and supergiants, massive stars that burn bright and fast, living only millions of years before exploding as supernovae. Each of these stars potentially has planets. While we can't directly observe planets around Andromeda's stars due to the distance involved, statistical studies of stars in our own galaxy suggest that most stars host at least one planet. If this holds true for Andromeda, we're talking about 1 trillion or more planets. ranging from small rocky worlds to massive gas giants, from frozen ice balls to scorching lava planets orbiting close to their parent stars. How many of these planets might be Earth-like? How many might orbit in the habitable zone where liquid water could exist? How many might have developed life? We don't know, and at Andromeda's distance, we may never know directly. But the numbers are staggering. Even if only a tiny fraction of 1% of stars have Earth-like planets in their habitable zones, we're still talking about billions of potentially habitable worlds in Andromeda alone. The interstellar medium. Between the stars of Andromeda lies the interstellar medium, a mix of gas and dust that fills the space between suns. Don't let the word medium fool you into thinking this is somehow dense or substantial. By Earth standards, the interstellar medium is an almost perfect vacuum, with only a few atoms per cubic centimetre in most regions. For comparison, the air you're breathing right now contains about 10 Balvin-19 molecules per cubic centimetre. The interstellar medium is emptier than the best vacuum we can create in laboratories on Earth. And yet, accumulated across the vast scale of a galaxy, this near-nothingness becomes significant. The total mass of gas and dust in Andromeda is estimated at several billion times the mass of our Sun. This material is not uniformly distributed. It clumps and concentrates in regions where gravity pulls it together, where shock waves from supernova explosions compress it, where density waves in the spiral arms squeeze it. In these denser regions, the interstellar medium becomes nurseries for new stars. Giant molecular clouds, some spanning hundreds of light-years across, harbour cold, dense cores where gravity finally overcomes the outward pressure and collapses the gas into new stars. This process is happening right now in Andromeda, creating thousands of new stars every year, even as old stars die and return their material to the interstellar medium to begin the cycle anew. When we observe Andromeda through a telescope, particularly an infrared light that can penetrate dust, we see these star-forming regions glowing with the heat of stellar birth. We see supernova remnants, the expanding shells of gas from stars that exploded, enriching the interstellar medium with heavy elements forged in stellar cores. We see the intricate structure of the spiral arms picked out in the light of ionized hydrogen, marking regions where massive young stars are flooding their surroundings with ultraviolet radiation. This is the living galaxy, not a static structure, but a dynamic evolving system where matter cycles between stars and interstellar space, where new stars are born and old stars die, where the chemical composition gradually enriches over billions of years as successive generations of stars forge heavier and heavier elements. Part 3. Measuring Andromeda. The distance problem. The historical challenge. For most of human history, we had no idea what Andromeda was. Ancient Persian astronomers noticed it as a faint smudge in the sky and recorded it in their catalogues. Medieval European astronomers saw it too, describing it as a little cloud in the constellation of Andromeda. But without telescopes, without any way to resolve it into individual stars or measure its distance, it remained mysterious. When telescopes first revealed that this fuzzy patch contained structure, astronomers initially called it a nebula, Latin for cloud. The question that dominated astronomical debate for centuries was deceptively simple. Was Andromeda part of our own Milky Way, a cloud of gas and perhaps stars within our galaxy? Or was it something far more distant, perhaps even another galaxy entirely separate from our own? This question, known as the Great Debate, wasn't settled until the 1920s, and the story of how we finally determined Andromeda's true distance and nature is one of the most fascinating chapters in the history of astronomy. The Cepheid variable solution. The breakthrough came through the work of Henrietta Leavitt, an astronomer working at Harvard College Observatory in the early 1900s. Leavitt was studying a class of stars called Cepheid variables, stars that brighten and dim in a regular, predictable pattern. What Leavitt discovered was revolutionary. There was a direct relationship between a Cepheid variable's period of pulsation and its intrinsic brightness or luminosity. This might not sound earth-shattering at first, but consider what it means. If you know a star's intrinsic brightness and you can measure how bright it appears from Earth, you can calculate exactly how far away it must be. The apparent brightness falls off with the square of the distance. So a star that's twice as far away appears 1/4 as bright. A star 3 times as far appears 1/9 as bright, and so on. Cepheid variables became the first reliable cosmic distance markers, standard candles, that allowed astronomers to measure distances across the universe. In 1923 and 1924, Edwin Hubble, using what was then the world's most powerful telescope at Mount Wilson Observatory, managed to resolve individual stars in Andromeda's outer regions. Among these stars, he identified several Cepheid variables. By measuring their periods and apparent brightnesses and using Leavitt's period-luminosity relationship, Hubble calculated that Andromeda was approximately 900,000 light-years away. This number, we now know, was significantly underestimated due to calibration errors in the period-luminosity relationship and the presence of interstellar dust that Hubble didn't account for. Modern measurements place Andromeda at about 2.5 million light-years distant. But even Hubble's underestimate was revolutionary, because it definitively proved that Andromeda was far outside our own Milky Way, making it an entirely separate galaxy. This discovery fundamentally transformed our understanding of the universe. In one stroke, the cosmos expanded from a single galaxy, our Milky Way, to a universe containing countless galaxies scattered through space. The implications were staggering and are still being absorbed today. Modern distance measurements. Today's astronomers have refined our measurement of Andromeda's distance using multiple independent methods, all of which converge on a value of about 2.537 million light-years, give or take about 30,000 light-years. This uncertainty might seem large. 30,000 light-years is about 1/3 the diameter of our entire Milky Way galaxy. But on the scale of intergalactic distances, it represents an uncertainty of only about 1%, which is remarkably precise. How do we measure such distances? Modern astronomers use a variety of techniques. Cepheid variables remain important, but we've refined our understanding of the period-luminosity relationship and can now account for factors like interstellar extinction from dust. We also use other standard candles, including RR Lyrae variables, another type of pulsating star, and even type Ia supernovae, exploding stars that reach a consistent peak brightness and can be seen across vast distances. We've also employed techniques that don't rely on standard candles at all. For instance, by measuring the proper motion of Andromeda, its movement across the sky relative to more distant background galaxies, and combining this with radial velocity measurements from spectroscopy, astronomers can use geometry and trigonometry to estimate distance. These different methods, based on entirely different physical principles, all agree on Andromeda's distance to within the measurement uncertainties. This convergence of evidence is powerful. When multiple independent methods of measurement all point to the same answer, we can be confident that we're not being fooled by systematic errors or incorrect assumptions about any single technique. What 2.5 million light-years means. So Andromeda sits at a distance of 2.5 million light-years. We've said this several times now, but let's really try to internalize what this means. The light you see when you look at Andromeda tonight left that galaxy 2.5 million years ago. To put this in human historical context, that light began its journey to your eyes before our species existed. The earliest members of the genus Homo were just beginning to emerge in Africa. The climate was different. The continents were in slightly different positions due to tectonic drift, and the entire configuration of life on Earth was alien compared to today. That light has been traveling toward you every second of every minute of every hour of every day for 2.5 million years. It passed the point where our solar system now orbits about 50,000 years ago, during the last ice age, when Neanderthals still walked the Earth. It crossed into the outer reaches of our solar system, the Oort cloud, perhaps 10,000 years ago, around the time humans were inventing agriculture. For all of recorded human history, for every war and empire, every invention and discovery, every birth and death, this light has been completing the final leg of its ancient journey. And here's something even more remarkable to consider. Because light takes time to travel, when we look at distant objects, we're looking back in time. When you observe Andromeda, you're not seeing it as it is right now in this moment. You're seeing it as it was 2.5 million years ago. For all we know, some catastrophic event might have occurred in Andromeda yesterday, but we won't know about it for another 2.5 million years because the light carrying that information hasn't reached us yet. In a very real sense, we can never know what Andromeda is doing right now. We are forever separated from its present state by the light travel time, condemned to observe only its ancient history. This is true for all astronomical observations. Of course, we even see our own sun as it was 8 minutes ago, but the effect becomes profound at galactic distances. Part 4. The size of Andromeda, diameter and structure. The visible extent. Now we come to the heart of our journey. How big is Andromeda really? The visible disk of Andromeda, the part we can see in telescopes containing the concentrated glow of its trillion stars, extends approximately 220,000 light-years in diameter. This makes Andromeda roughly 20 to 60% larger than our own Milky Way, depending on exactly how we define the edge of each galaxy. Let's build up an understanding of this measurement step by step, using the mental scaffolding we've already constructed. Remember that our Milky Way galaxy is about 100,000 to 180,000 light-years across. Andromeda is significantly larger, so let's use the 220,000 light-year measurement. If we placed our Sun at one edge of Andromeda's visible disk and travelled in a straight line at the speed of light, it would take us 220,000 years to reach the opposite edge. Think about that journey. You would leave the edge of Andromeda when modern humans were just beginning to spread out of Africa, and you would arrive at the opposite edge in the present day, having witnessed the entire story of our species' expansion across the globe, the rise and fall of countless civilizations, the extinction of megafauna, ice ages coming and going, all from the perspective of light crossing a single galaxy. Now let's approach this from a different angle to make it even more concrete. Imagine we could build a scale model where we shrink distances down to something manageable. Let's say we represent the Earth as a tiny grain of sand, about 1 millimeter across. On this scale, the Sun would be a ball about 11 centimeters in diameter, roughly the size of a grapefruit, sitting about 12 meters away from our grain of sand Earth. On this same scale, the nearest star, Proxima Centauri, would be another grapefruit-sized ball, sitting about 3,200 kilometers away. That's roughly the distance from New York to Los Angeles. Our entire Milky Way galaxy on this scale would span about 75 million kilometers, which is roughly half the distance from the Earth to the Sun in actual measurements. And Andromeda? Andromeda's visible disk on this scale would be about 165 million kilometers across, sitting at a distance of about 187 billion kilometers from our scaled-down Milky Way. At this scale, the distance between the two galaxies would be greater than the actual distance from the Sun to Neptune, multiplied by over 1,000 times. These comparisons start to break down because the numbers remain incomprehensibly large, even when we shrink them. This is the fundamental problem we keep encountering. The human mind simply didn't evolve to hold these scales comfortably. The structure in 3 dimensions. When we talk about Andromeda being 220,000 light-years across, we're usually referring to its extent as seen from our viewpoint here on Earth. But Andromeda is a 3-dimensional object, and understanding its structure in depth adds another layer to our appreciation of its size. Andromeda appears to us tilted at an angle of about 77 degrees from edge on. If we could see it perfectly edge on, it would look like a thin line of light, just the edge of its disk. If we saw it perfectly face on, we'd see the full spiral structure spread out like a pinwheel. The actual viewing angle of 77 degrees means we see it nearly edge on, but with just enough tilt that we can make out the spiral structure. The disk of Andromeda, where most of its stars reside, is remarkably thin compared to its diameter. The disk is only about 10,000 light-years thick at its thickest point, and even thinner in the outer regions. This means Andromeda's disk has a diameter-to-thickness ratio of about 22:1. If you built a scale model of Andromeda where the galaxy was the size of a large pizza, about 14 inches across, the disk would be less than 2/3 of an inch thick. This thinness tells us something important about how galaxies form and maintain their structure. The thin disk is a consequence of rotation and angular momentum conservation. When the gas that would eventually form Andromeda's disk collapsed under its own gravity, it couldn't collapse equally in all directions because it was rotating. Rotation prevented collapse perpendicular to the rotation axis, creating the flattened disk we observe. Surrounding this thin disk is the galactic bulge, the central concentration of stars that gives Andromeda its bright core. This bulge is roughly spherical and extends about 10,000 to 12,000 light-years from the galactic center. The stars in the bulge are predominantly older, redder stars, populations that formed billions of years ago when the galaxy was young. Beyond the disk and bulge lies the stellar halo, a diffuse, roughly spherical distribution of old stars and globular clusters that extends far beyond the visible disk. Globular clusters are dense spherical collections of hundreds of thousands to millions of stars, thought to be among the oldest structures in galaxies. Andromeda has somewhere between 450 and 500 known globular clusters, and they extend out to distances of 300,000 light-years or more from the galactic center, well beyond the main stellar disk. Comparing Andromeda to the Milky Way. It's natural to compare Andromeda to our own galaxy, and doing so helps us understand both systems better. The Milky Way and Andromeda are the two dominant members of what we call the local group, a collection of more than 50 galaxies bound together by gravity. Andromeda is the larger of the two in terms of diameter and stellar mass. While our Milky Way contains somewhere between 200 and 400 billion stars, Andromeda boasts about 1 trillion stars, roughly 2 to 5 times as many. This makes Andromeda significantly more massive in terms of stellar content. However, when you include dark matter, the comparison becomes more nuanced. Some recent studies suggest that the Milky Way's dark matter halo might actually be more massive than Andromeda's, which would make our galaxy the more massive of the two overall, despite having fewer stars. This is still a matter of active research and some debate in the astronomical community. Both galaxies show evidence of having cannibalized smaller galaxies in their past. Andromeda, in particular, appears to have undergone a major merger with another large galaxy, perhaps 2 to 3 billion years ago. Evidence for this comes from computer simulations of galactic collisions, which can reproduce many of Andromeda's observed features, including a strange structure in its stellar halo and the presence of tidal streams, ribbons of stars torn from smaller satellite galaxies by Andromeda's gravity. The extended hydrogen disk. In the 1990s, astronomers made a surprising discovery when they observed Andromeda using radio telescopes tuned to detect neutral atomic hydrogen. They found that Andromeda's hydrogen gas extends far beyond the visible stars, creating a vast disk that reaches out to about 220,000 light-years from the galactic center, making the total extent of the hydrogen disk approximately 440,000 light-years across, double the extent of the visible stellar disk. This extended hydrogen disk is remarkably thin and tenuous, containing relatively little mass compared to the central regions. But its presence tells us that galaxies don't have sharp edges. Instead, they fade gradually, thinning out until the density of material becomes indistinguishable from the intergalactic medium. Even more remarkably, some of this extended hydrogen appears to have been stripped from satellite galaxies as they orbit Andromeda. Like water being pulled off a swimmer by air resistance as they move through the air, the intergalactic medium exerts a drag force on smaller galaxies as they orbit through the tenuous halo of Andromeda, stripping gas from them in a process called ram pressure stripping. The dark matter halo. We've already touched on dark matter, but it's worth emphasizing just how much the dark matter halo extends Andromeda's total size. While the visible stars extend out to about 110,000 light-years from the galactic center, and the hydrogen gas reaches to perhaps 220,000 light-years, the dark matter halo extends far beyond both. Current models suggest Andromeda's dark matter halo extends out to at least 300,000 to 400,000 light-years from the galactic center, and possibly much farther. Some estimates place the effective edge of the dark matter halo at 600,000 to 800,000 light-years from Andromeda's center, at which point the density of dark matter has dropped to levels comparable to the cosmic mean. This means that the total gravitational structure of Andromeda, the complete three-dimensional region dominated by its gravity, might extend to more than 3 times the diameter of the visible galaxy. If we include this dark matter halo in our measurement, Andromeda isn't just large, it's absolutely enormous, spanning well over 1 million light-years from one edge of its dark matter halo to the other. This extended dark matter halo has profound implications for Andromeda's interactions with its surroundings. The Milky Way and Andromeda are rushing toward each other at about 110 kilometers per second, or roughly 250,000 miles per hour. At a separation of 2.5 million light-years, you might think they're far apart. But when you consider that their dark matter halos might each extend for 800,000 light-years or more, the halos are already beginning to overlap. The two galaxies are already touching. In a sense, their dark matter halos interacting gravitationally, even though their visible stellar disks remain separated by millions of light-years of space. Part 5. The Satellite System, Andromeda's Family, the Local Group Context. To fully appreciate Andromeda's size and influence, we need to zoom out and see it in context. Andromeda doesn't exist in isolation. It's the gravitational anchor for a significant portion of the local group, a collection of galaxies bound together by their mutual gravity. The local group contains more than 50 known galaxies spread across a region of space about 10 million light-years in diameter. Most of these are small dwarf galaxies, some containing only a few million stars. But a few are substantial objects in their own right. Besides the Milky Way and Andromeda, the only other galaxy of significant size in the local group is Triangulum, also known as M33. a spiral galaxy about 60 billion solar masses sitting roughly 3 million light-years from us and about 750,000 light-years from Andromeda. The local group is divided into two main concentrations of galaxies. One group orbits the Milky Way, including the Large and Small Magellanic Clouds, two small irregular galaxies visible to the naked eye from the southern hemisphere. The other concentration orbits Andromeda, and Andromeda's family is significantly larger than ours. Andromeda's satellite galaxies. Andromeda is known to have at least 14 satellite galaxies. The largest of these is M32, also known as NGC 221, a compact elliptical galaxy sitting about 2.7 million light-years from us, but only about 200,000 light-years from Andromeda itself. M32 is unusual for a satellite galaxy because it's quite luminous and massive, containing perhaps 3 billion stars. Another prominent satellite is M110, or NGC 205, a dwarf elliptical galaxy sitting on the opposite side of Andromeda from M32. M110 contains about 10 billion stars and, like M32, is readily visible in moderate-sized amateur telescopes as a fuzzy patch near Andromeda's disk. But the really interesting satellites are the dwarf galaxies. These small, faint galaxies are dominated by dark matter and contain relatively few stars. Andromeda Y, for example, is a dwarf spheroidal galaxy sitting about 2.6 million light-years from us. It contains only about 10 million stars spread across a volume of space several thousand light-years across. This makes it incredibly diffuse, with stars separated by such vast distances that the night sky from a planet in Andromeda I would look nearly empty, devoid of the rich star fields we see from Earth. Many of Andromeda's satellite galaxies were only discovered in the past few decades as digital camera technology improved and allowed astronomers to detect extremely faint, diffuse objects. There are almost certainly more satellites waiting to be discovered, particularly at large distances from Andromeda, where they would be extremely faint and difficult to distinguish from background galaxies. Tidal streams and galactic cannibalism. Perhaps the most dramatic evidence of Andromeda's gravitational influence comes from tidal streams, vast ribbons of stars wrapped around the galaxy. These streams are the remnants of dwarf galaxies that wandered too close to Andromeda and were torn apart by tidal forces. Tidal forces arise because gravity weakens with distance. When a small galaxy approaches a large galaxy like Andromeda, the side of the small galaxy closer to Andromeda feels a stronger gravitational pull than the far side. This difference in gravitational force stretches the small galaxy, pulling it into an elongated shape. If the tidal forces are strong enough, they can completely overcome the small galaxy's self-gravity, tearing it apart and spreading its stars into a long stream orbiting the larger galaxy. Andromeda has several well-documented tidal streams. The most prominent, sometimes called the Giant Stellar Stream, extends for hundreds of thousands of light-years around Andromeda. Detailed studies of the stars in this stream reveal that they came from multiple smaller galaxies that were consumed by Andromeda over the past few billion years. These tidal streams are important for several reasons. First, they demonstrate that galaxy growth is an ongoing process. Andromeda didn't form all at once and then remain static. It continues to grow by accreting smaller galaxies, a process that will likely continue for billions of years into the future. Second, the patterns of tidal streams preserve information about Andromeda's gravitational field, including the distribution of dark matter. By studying how streams wrap around the galaxy, astronomers can map out the shape and extent of the dark matter halo with greater precision than would otherwise be possible. Third, these streams remind us that galaxies are not isolated objects, but exist in a cosmic ecosystem where they interact with, consume, and merge with one another in a complex dance orchestrated by gravity across billions of years. The sphere of influence. An interesting question to ask is, how far does Andromeda's gravitational influence extend? At what distance does another object escape Andromeda's gravitational dominance and become, in effect, free? This is a more complex question than it might first appear, because Andromeda doesn't exist in isolation. It's part of the local group, which means other galaxies, particularly the Milky Way, exert their own gravitational influences. Between Andromeda and the Milky Way, there's a point called the zero-velocity surface, where the gravitational pull from both galaxies is equal. Objects beyond this surface are gravitationally bound to one galaxy or the other. For Andromeda, this sphere of influence extends roughly 1 million light-years from its centre, meaning any object within this radius is primarily under Andromeda's gravitational control and will eventually fall into the galaxy unless something intervenes. To put this in perspective, if we define Andromeda's size as its sphere of gravitational dominance, then it's about 2 million light-years in diameter. This is nearly as large as the current distance between Andromeda and the Milky Way, which emphasizes just how much these two galaxies are already influencing each other gravitationally, despite the millions of light-years separating their visible disks. Part 6. Observing Andromeda, What We Can See. The Naked Eye. View. One of the most remarkable things about Andromeda is that you can see it with your naked eye from a reasonably dark location. This means that without any technological assistance whatsoever, you can look up at the night sky and observe photons that travelled for 2.5 million years across the intergalactic void to reach your eyes. From a dark sight, Andromeda appears as a faint, fuzzy oval patch, about 6 times the width of the full moon in the sky. Yes, you read that correctly. The angular size of Andromeda on the sky is actually quite large, about 3 degrees long and 1 degree wide. The full moon, for comparison, is about half a degree across. Why then doesn't Andromeda look larger and more impressive to the naked eye? The answer is that it's extremely dim. The light from Andromeda's trillion stars is spread across that large area, making the surface brightness, the brightness per unit area of sky, very low. Your eye and brain are much better at detecting compact, bright objects than diffuse, faint ones. So even though Andromeda spans a considerable arc of sky, you perceive it as a small, faint smudge. Under truly dark skies, with excellent visibility and dark-adapted eyes, experienced observers can sometimes make out hints of Andromeda's structure with the naked eye, detecting the brighter central regions and perhaps a slight elongation indicating the disk. But for most people, even in good conditions, it looks like nothing more than a fuzzy star. The fact that we can see it at all is testament to its sheer luminosity. Andromeda emits approximately 25 billion times more light than our Sun. Despite being 2.5 million light-years away, enough of this torrent of light reaches Earth that even the limited light-gathering capability of the human eye can detect it. Through binoculars and small telescopes. Viewing Andromeda through binoculars or a small telescope transforms it from a faint smudge to a genuine celestial object with visible structure. Even a modest pair of 7x50 binoculars will reveal Andromeda's elongated shape and bright central region. The galaxy takes on a distinct oval appearance, and you can begin to appreciate its orientation on the sky. With a small telescope, say a 6-inch or 8-inch aperture reflector, considerably more detail emerges. The bright central bulge becomes prominent, and in good conditions you can trace the disk out to significant distances from the core. Dark lanes of dust become visible, particularly one prominent dust lane that cuts across one side of the galaxy, blocking light from stars behind it. The two largest satellite galaxies, M32 and M110, are also readily visible in small telescopes as faint fuzzy patches near Andromeda's disk. M32 appears as a bright, compact ellipse, while M110 is more diffuse and elongated. One of the fascinating aspects of observing Andromeda through a telescope is that you're not seeing the galaxy as a single object all at once. Remember, the galaxy is 220,000 light-years across. This means the light from the near edge of Andromeda's disk left the galaxy about 110,000 years before the light from the far edge. You're seeing different parts of the galaxy as they existed at different times, with a time difference of over 200,000 years between the nearest and farthest visible regions. Of course, 200,000 years is short compared to the timescales on which galaxies evolve, so this doesn't produce any noticeable effect. But it's a conceptually interesting point. When you observe a galaxy, you're not seeing a snapshot of a moment in time, but rather a composite image assembled from light that left different parts of the object at different times. Long exposure photography. The real beauty of Andromeda emerges in long exposure photographs, where cameras can accumulate light for minutes or hours to reveal details invisible to the eye. In deep photographs, Andromeda's spiral structure becomes clearly visible. You can trace the spiral arms as they wind outward from the central bulge, see the blue-white light of young star clusters dotting the arms, and observe the reddish glow of star-forming regions where hydrogen gas is ionized by ultraviolet radiation from hot young stars. The dust lanes become more prominent in deep images, showing the intricate structure of dust clouds silhouetted against the background glow of stars. These dust lanes are regions where new stars are being born, hidden from optical view but detectable in infrared light that can penetrate the dust. Modern amateur astronomers with high-quality cameras and tracking mounts can produce images of Andromeda that rival professional photographs from decades ago. Some of these images reveal tidal streams, faint shells of stars surrounding the galaxy, and even individual star clusters within Andromeda's disk. Professional observatories with large telescopes and sensitive detectors can resolve individual stars in Andromeda, at least in the outer regions where stars are less densely packed. The Hubble Space Telescope has imaged portions of Andromeda in extraordinary detail, revealing hundreds of millions of individual stars. One particular Hubble image, released in 2015, captured a section of Andromeda spanning about 40,000 light-years and containing over 100 million stars. The image contained 1.5 billion pixels and represented over 600 hours of exposure time. When you zoom into this Hubble image, you can see individual stars with different colors: red giants, blue giants, yellow sun-like stars. Each dot of light in the image is a sun, potentially with planets, possibly even with civilizations looking back at us across the intergalactic gulf. Across the electromagnetic spectrum, optical light, the light our eyes can see, represents only a tiny fraction of the electromagnetic spectrum. Andromeda emits radiation across the entire spectrum, from radio waves meters long to gamma rays smaller than atomic nuclei. By observing Andromeda at different wavelengths, we can see different aspects of the galaxy and learn things that would be impossible from optical observations alone. In radio waves, Andromeda reveals its magnetic fields and the synchrotron radiation emitted by electrons spiraling around magnetic field lines. Radio observations also trace the distribution of neutral atomic hydrogen and molecular gas, showing where the raw material for star formation is concentrated. In infrared light, we see the heat glow from dust warmed by nearby stars. Infrared observations penetrate the dust lanes that block optical light, revealing the star formation hidden behind them. The Spitzer Space Telescope and the Herschel Space Observatory have mapped Andromeda in infrared, showing intricate details of dust lanes and star-forming regions. In ultraviolet light, we see the hottest, youngest, most massive stars. These stars burn bright and fast, living only millions of years before exploding as supernovae. Ultraviolet observations pick out regions of recent star formation and trace the structure of the spiral arms, where these massive stars are concentrated. In X-rays, Andromeda lights up with sources like X-ray binaries, systems where a normal star orbits a neutron star or black hole, transferring matter onto the compact object and producing intense X-ray emission. The Chandra X-ray Observatory has catalogued hundreds of X-ray sources in Andromeda, each one representing an exotic stellar remnant or an active galactic nucleus. Each wavelength reveals a different aspect of Andromeda, and only by combining observations across the electromagnetic spectrum can we build a complete picture of the galaxy's structure, composition, and dynamics. Part 7. The Future. Collision Course. The Inevitable Merger. As I mentioned at the beginning of our journey, Andromeda and the Milky Way are on a collision course. Astronomers have known for decades that Andromeda is approaching us, and we've recently refined our measurements to determine not just that a collision will occur, but when and how. Andromeda is currently moving toward the Milky Way at a velocity of about 110 kilometers per second, or roughly 250,000 miles per hour. At this speed, you might expect the two galaxies to collide relatively quickly. After all, they're only 2.5 million light-years apart, and if one is moving toward the other at a decent fraction of the speed of light, shouldn't the collision happen soon? But space is vast, and even at 110 kilometers per second, it will take about 4 billion years for Andromeda to reach us. To put this in context, 4 billion years ago, Earth had only just become hospitable to life. The first single-celled organisms were emerging in ancient oceans. Everything that has happened in the history of life on Earth, from those first simple cells to fish, to amphibians, to reptiles, to dinosaurs, to mammals, to humans, all of it has occurred in less time than it will take for Andromeda to reach us. In 4 billion years, the Sun will be noticeably hotter and brighter than it is today, potentially making Earth uninhabitable even before the galactic collision occurs. Any civilization still existing on Earth at that time, whether human or whatever our descendants evolve into, will have had billions of years to prepare for the merger. The collision dynamics. Despite the name galactic collision, individual stars almost certainly won't collide. Galaxies are mostly empty space. Remember that the distance between stars in a galaxy is enormous compared to the sizes of the stars themselves. Even when two galaxies merge, passing right through each other, the probability of any two stars actually colliding is vanishingly small. What will happen instead is far more interesting and in some ways more dramatic. As the two galaxies approach, their gravitational fields will begin to interact strongly. Tidal forces will distort both galaxies, pulling them into elongated shapes. Stars will be flung out of their normal orbits, some gaining enough energy to escape both galaxies entirely, while others will be hurled into the merging core. Computer simulations of the collision suggest that the first close approach will occur in about 4 billion years. The two galactic disks will plunge through each other, with Andromeda's stars passing between the Milky Way's stars like two clouds of gnats interpenetrating. But the gravity of each galaxy will grab onto the other, and rather than continuing on their separate ways, both galaxies will be slowed and turned around by their mutual attraction. About 2 billion years after the first pass, the galaxies will fall back together for a second encounter, and then a third. With each pass, the two systems lose energy through a process called dynamical friction, gradually spiraling closer and closer together. Eventually, after perhaps 7 to 8 billion years total, the two galaxies will finally merge into a single structure. The final product will be an elliptical galaxy, a roughly spherical or football-shaped collection of stars with no remaining spiral structure. The merger will have scrambled the organized rotation of both spiral disks, leaving stars on chaotic orbits that collectively produce the spheroidal shape of an elliptical galaxy. This new merged galaxy, sometimes nicknamed Milkomeda in astronomy popular literature, will be quite different from either of its parent galaxies. It will be more massive, containing the combined stellar populations of both the Milky Way and Andromeda, something like 1.2 to 1.5 trillion stars. It will be larger in overall size, though perhaps not as large as you might expect, because the merger will actually make the stars pack more tightly together on average. Impact on our solar system. A question people often ask is, What will happen to Earth and our solar system during the merger? The honest answer is that we don't know for certain, because the collision is a chaotic process, and small variations in initial conditions can lead to very different outcomes. But we can make some educated guesses based on simulations. The most likely outcome is that our solar system will survive the collision largely intact. Remember that stars very rarely collide directly, and the chances of another star passing close enough to Earth to disturb our orbit significantly are small, though not zero. What will certainly change is the view from Earth's surface, assuming Earth still exists and has a surface at that point. As Andromeda approaches, it will grow larger in the night sky, eventually spanning tens of degrees and becoming the dominant feature of the nighttime heavens. During the merger itself, the sky will be ablaze with stars from both galaxies, with densities of stars in some regions becoming high enough that there might be no true night, even on the side of Earth facing away from the Sun. The merger will trigger massive bursts of star formation as gas clouds from the two galaxies collide and compress each other. These star-forming regions will glow brilliantly, and the massive stars born in them will live fast and explode as supernovae, potentially dozens or even hundreds of supernovae going off in relatively close proximity over the course of a few million years. Some simulations suggest that our solar system might be flung out into the outer reaches of the merged galaxy, or even ejected entirely, becoming an orphan solar system wandering through intergalactic space. Other simulations suggest we might be scattered into the central regions of the new galaxy, where stars are more densely packed. But through all of this, the Sun and Earth would likely remain bound together, and the planets would continue their orbits largely undisturbed. The merger is a catastrophic event on galactic scales, but to an individual star and its planets, it might pass almost unnoticed, except for the spectacular changes in the night sky. The longer-term future. After the merger completes, the newly formed elliptical galaxy will settle into a new equilibrium. Star formation will likely drop to very low levels because the merger will have used up or dispersed most of the available gas. The galaxy will be dominated by old red stars, slowly fading as the most massive stars die off and are not replaced. Over hundreds of billions of years, even the longest-lived stars will eventually exhaust their fuel. The galaxy will grow darker and darker as stars wink out one by one. Eventually, perhaps 1 trillion years from now, the galaxy will be a collection of dead stellar remnants, white dwarfs, neutron stars and black holes, no longer producing any significant light. But even this isn't the end. The merged galaxy will itself be part of a larger structure, the Virgo supercluster, and will eventually merge with other galaxies in an ongoing process of hierarchical structure formation that continues across cosmic time. Part 8. Andromeda and Humanity. Our connection to the cosmos. The historical connection. Andromeda has been known to humanity for thousands of years. Ancient Persian astronomers catalogued it as early as 964 CE. It appears in medieval Arabic astronomical texts. European astronomers in the 1600s and 1700s described it as a nebula, not understanding its true nature. But it was only in the 1920s, less than 100 years ago, that we understood what we were looking at. For thousands of years, humans observed Andromeda without comprehending that it was another galaxy, an island universe of stars comparable to our own Milky Way. This realization fundamentally changed our place in the cosmos. Before Hubble's observations proved Andromeda's extra-galactic nature, we thought the Milky Way was the entire universe. Yes, there were these mysterious spiral nebulae, but most astronomers believed they were within our galaxy, perhaps solar systems in formation or some other phenomenon occurring within the Milky Way's boundaries. When Hubble demonstrated that Andromeda was millions of light-years distant, the universe expanded in human consciousness by a factor of thousands in a single stroke. And it didn't stop there. If Andromeda was a galaxy beyond our own, then perhaps all those other spiral nebulae were galaxies too. Within a few years, it became clear that the universe contained millions, then billions of galaxies, each containing billions of stars. This expansion of cosmic perspective ranks among the most profound discoveries in human history, comparable to Copernicus's realization that Earth orbits the Sun, or Darwin's understanding that species evolve through natural selection. These are ideas that fundamentally restructure how we understand our place in the cosmos. The cosmic perspective. Looking at Andromeda, really understanding its scale and distance, provides what Carl Sagan called the cosmic perspective. This is the understanding that Earth is a tiny world in a vast universe, that our Sun is one among hundreds of billions in our galaxy, and our galaxy is one among hundreds of billions in the observable universe. Some people find this perspective depressing or nihilistic. If we're so insignificant compared to the cosmos, they ask, does anything we do matter? But I think this gets it backwards. Yes, we're small compared to galaxies, but we're also the only things we know of that can understand galaxies. As far as we know, we're the only consciousness in the universe capable of looking at Andromeda and comprehending what it is, measuring its distance, calculating its mass, predicting its future collision with our galaxy billions of years hence. In a very real sense, we are the universe's way of understanding itself. We are matter organized in such a way that it can contemplate matter, atoms arranged such that they can study atoms, star stuff that has evolved to the point where it can investigate stars. This is extraordinary. You, sitting here right now, reading these words, are made of atoms forged in the cores of stars that exploded billions of years ago. The calcium in your bones, the iron in your blood, the oxygen you breathe, all were created in stellar furnaces and scattered through space when those stars died. You are literally made of star stuff. And now you're using that star stuff to understand stars and galaxies. The quest to understand. Scale. Our entire journey today has been an attempt to understand scale, to build mental models that can encompass the truly vast. This is, in many ways, what science does. Science gives us tools to understand things that lie beyond direct human experience. We can't directly perceive atoms, but we can build models and instruments that let us understand them. We can't directly sense infrared light or X-rays, but we can build detectors that translate these invisible radiations into something our eyes and brains can process. We can't directly comprehend 1 trillion stars spread across 220,000 light-years, but we can build analogies, scale models, and mathematical frameworks that make these cosmic enormities accessible to human minds. This is one of humanity's great achievements, our ability to extend our understanding beyond the limits of our senses and our immediate experience. We're primates who evolved to navigate trees and savannas, to hunt, gather, cooperate and communicate. And yet we've developed the conceptual tools to understand galaxies, black holes, the Big Bang, the structure of DNA, the quantum nature of reality. Where do we go from here? Understanding Andromeda's size is more than an academic exercise. It connects us to the cosmos in a visceral way. It challenges us to think bigger, to expand our perspective, to recognize our place in a universe far vaster and more ancient than everyday experience suggests. Where does this understanding lead? For some people, it leads to a career in science, a life dedicated to pushing the boundaries of human knowledge further. For others, it simply enriches their experience of the night sky, transforming what might seem like random dots of light into a three-dimensional cosmos full of structure and meaning. In a practical sense, understanding cosmic scale helps us appreciate just how precious and rare Earth might be. When you truly understand the distances between stars, you realize that interstellar travel is extraordinarily difficult. When you comprehend that there might be billions of planets in Andromeda alone, you begin to wonder whether any of them harbor life, and if so, whether we'll ever know. These are questions that may take centuries or millennia to answer, but they're questions worth asking. And they only become meaningful when you first grasp the scale involved. Part 9. Advanced Topics Diving Deeper. The Nature of Dark Matter. We've mentioned dark matter several times, but let's explore it in more depth, because it's central to understanding Andromeda's true size and mass. Dark matter, despite making up roughly 85% of all matter in the universe, remains one of the greatest mysteries in modern physics. We know it exists from its gravitational effects. We can see it bending light through gravitational lensing. We can measure how it affects the rotation of galaxies, but we have no idea what it actually is. It's not made of atoms like normal matter. We know this because if it were, it would interact with light and we'd be able to see it. It's not black holes or other dark objects made of normal matter because we can account for those separately and the numbers don't work out. The leading hypothesis is that dark matter consists of particles that don't interact electromagnetically, meaning they don't emit, absorb, or reflect light. These hypothetical particles interact only through gravity and possibly through the weak nuclear force. Many experiments around the world are currently trying to detect dark matter particles, but so far none have succeeded. In Andromeda, the dark matter halo contains perhaps 6 to 8 times as much mass as all the visible stars combined. This invisible mass shapes the galaxy's structure, determines how fast stars orbit, and controls how Andromeda interacts gravitationally with other galaxies. Understanding dark matter is crucial to understanding galaxy formation and evolution. Computer simulations of galaxy formation start with distributions of dark matter, because the dark matter creates the gravitational wells into which normal matter falls. The dark matter forms the invisible scaffolding upon which visible galaxies are built. Stellar populations and galactic archaeology. When we look at Andromeda, we're seeing a complex mix of stellar populations, different groups of stars that formed at different times, and from gas with different chemical compositions. Population I stars are young, metal-rich stars found predominantly in the galactic disk and spiral arms. In astronomy, any element heavier than hydrogen and helium is called a metal, even though chemists might object to calling oxygen or carbon metals. Population I stars formed relatively recently from gas that had already been enriched with heavy elements from previous generations of stars. Population II stars are old, metal-poor stars found predominantly in the galactic bulge and halo. These stars formed early in the galaxy's history from gas that had seen little previous star formation, and thus had low abundances of heavy elements. By studying the mix of stellar populations in different parts of Andromeda, astronomers can reconstruct the galaxy's formation history. It's a bit like archaeology, but instead of digging through layers of Earth to uncover ancient civilizations, we're analyzing the colors and spectra of stars to uncover ancient stellar generations. What this galactic archaeology reveals is that Andromeda, like most large galaxies, formed through a complex process involving the merger of smaller galaxies over billions of years. The evidence is written in the stellar populations, in the tidal streams, in the strange features visible in deep images. The central black hole. At the heart of Andromeda sits a supermassive black hole with a mass of roughly 100 to 200 million times that of our Sun. This might sound enormous, and it is, but it represents only about 0.01% of the galaxy's total stellar mass. Despite being such a small fraction of the total, this black hole plays an important role in the galaxy's evolution. Supermassive black holes are found at the centers of virtually all large galaxies. The relationship between the mass of the central black hole and the mass of the galactic bulge is surprisingly tight, suggesting a deep connection between black hole growth and galaxy formation. Andromeda's central black hole is currently relatively quiet. It's not actively consuming large amounts of material and doesn't produce the enormous jets and radiation that we see in some active galactic nuclei. But it's still there, and occasionally a star or gas cloud that wanders too close gets torn apart and consumed, producing brief flares of radiation that we can detect with specialized instruments. Interestingly, there's evidence that Andromeda's central black hole might actually be a binary system, two supermassive black holes orbiting each other at the galaxy's core. This could be the result of a past galaxy merger where both galaxies brought their central black holes to the collision. Over time, these black holes spiral inward and eventually merge, producing gravitational waves so powerful that they ripple the very fabric of space-time across the universe. Star formation history. Andromeda is still forming new stars, though at a relatively modest rate compared to some galaxies. Current estimates suggest Andromeda produces about 1 solar mass worth of new stars per year. For comparison, our Milky Way produces about 2 to 3 solar masses of new stars per year. So Andromeda is actually less actively star-forming than our own galaxy, despite being larger. This might seem surprising, but it reflects the fact that Andromeda has used up much of its available star-forming gas. The rate of star formation in a galaxy depends on the amount of cold, dense molecular gas available, and while Andromeda has plenty of total gas, much of it is too hot or too diffuse to collapse into new stars. The star formation that does occur is concentrated in rings around the galactic center and in the spiral arms, where density waves compress the gas and trigger gravitational collapse. Observations in ultraviolet and infrared light reveal thousands of star-forming regions scattered throughout Andromeda's disk, each one a stellar nursery where dozens or hundreds of new stars are condensing out of the interstellar gas. The history of star formation in Andromeda has been anything but steady. Evidence suggests major bursts of star formation in the past, likely triggered by galaxy mergers. When two galaxies collide, their gas clouds slam into each other, compressing and shocking the gas and triggering enormous waves of star formation that can increase the star formation rate by factors of 10 or even 100 for a few 100 million years. One particularly interesting feature visible in deep images of Andromeda is a series of rings or shells of stars around the galactic disk. These structures are thought to be the remnants of smaller galaxies that Andromeda consumed in its past, their stars now spread into faint rings encircling the main galaxy. Computer simulations can reproduce these features and suggest that Andromeda may have experienced a major merger with another large galaxy about 2 to 3 billion years ago. Metallicity gradients and chemical evolution. As stars form, live their lives and die, they change the chemical composition of the galaxy. Massive stars, in particular, produce heavy elements through nuclear fusion in their cores, and then scatter these elements into space when they explode as supernovae. Over time, the interstellar medium becomes progressively enriched with heavy elements, so each new generation of stars forms from gas that's more metal-rich than the previous generation. This process creates metallicity gradients in galaxies. In Andromeda, as in most spiral galaxies, the central regions are more metal-rich than the outer regions. This is because star formation has been ongoing for longer and at higher rates in the center, leading to more chemical enrichment. By mapping the metallicity across Andromeda, astronomers can trace the galaxy's chemical evolution, understanding how the mix of elements has changed over time and varies with position. This provides insights into the rate of star formation at different times and locations, the efficiency with which supernovae mix their heavy elements into the interstellar medium, and the inflow and outflow of gas. Remarkably, some individual stars in Andromeda can be studied spectroscopically, allowing astronomers to measure their chemical compositions directly. The largest telescopes in the world, like the Keck telescopes in Hawaii and the Very Large Telescope in Chile, can obtain spectra of individual stars in Andromeda, even though those stars are 2.5 million light-years away. This is an extraordinary technical achievement and provides a powerful tool for understanding the galaxy's history. Part 10. Comparative Galactology. Andromeda in context. Andromeda versus other galaxies. To fully appreciate Andromeda's size, it helps to compare it to other galaxies across the universe. In the realm of spiral galaxies, Andromeda is definitely large, but not the largest. Some spiral galaxies are significantly bigger. NGC 6872, for example, is a barred spiral galaxy about 522,000 light-years across, more than twice the diameter of Andromeda. UGC 2885, nicknamed Rubin's Galaxy after astronomer Vera Rubin, spans about 463,000 light-years. But these extra-large spirals are relatively rare. Andromeda is much larger than the typical spiral galaxy, which tends to measure 50,000 to 100,000 light-years across. In this sense, Andromeda represents the upper tier of spiral galaxies, a massive example of the type rather than a typical one. When we look at elliptical galaxies, the size comparisons become even more dramatic. The largest elliptical galaxies, called giant ellipticals or CD galaxies, found at the centers of galaxy clusters, can be enormous. IC 1101, one of the largest known galaxies, is an elliptical galaxy measuring approximately 4 to 6 million light-years across, about 20 to 30 times the diameter of Andromeda. These giant ellipticals formed through multiple mergers of smaller galaxies over billions of years. They sit at the centers of massive galaxy clusters, the gravitational anchor points for hundreds or even thousands of other galaxies. Compared to these monsters, Andromeda is relatively modest. On the smaller end of the scale, dwarf galaxies can be remarkably tiny. Some dwarf spheroidal galaxies measure only a few thousand light-years across and contain only a few million stars. The smallest dwarf galaxies blur the line between galaxy and star cluster, containing so few stars that it's debatable whether they deserve the name galaxy at all. The local group, and beyond Andromeda, sits within the local group, a gravitationally bound collection of galaxies that represents our cosmic neighborhood. But the local group itself is just one small structure in a much larger hierarchy. The local group is part of the Virgo supercluster, also called the local supercluster, a vast collection of galaxy groups and clusters spanning about 110 million light-years. At the heart of this supercluster sits the Virgo cluster, a dense collection of over 1,500 galaxies dominated by the giant elliptical 87. Recent mapping efforts using new techniques to measure galaxy motions have revealed that the local group is actually part of an even larger structure called Laniakea, a supercluster of superclusters spanning about 520 million light-years and containing approximately 100,000 large galaxies. At this scale, Andromeda starts to seem almost insignificant. It's one large galaxy among 100,000 in Laniakea, which is itself just one supercluster among millions in the observable universe. The hierarchy keeps expanding. Galaxies form groups, groups form clusters, clusters form superclusters, and superclusters form even larger structures separated by vast cosmic voids where few galaxies exist. This cosmic web, as it's called, is the large-scale structure of the universe, and it represents the organization of matter on the absolute largest scales observable. Andromeda is one tiny thread in this vast tapestry. Why study Andromeda? Specifically, given that there are hundreds of billions of galaxies in the observable universe, why do astronomers pay so much attention to Andromeda specifically? The answer is proximity. Andromeda is close enough that we can study it in extraordinary detail, resolving individual stars, mapping the distribution of gas and dust, tracing stellar orbits, and detecting faint structures like tidal streams that would be invisible in more distant galaxies. Most galaxies are so far away that we can only study their overall properties. Total mass, star formation rate, chemical composition averaged across the entire galaxy. But with Andromeda, we can do galactic archaeology, piecing together its formation history from detailed observations of different stellar populations. Andromeda serves as a laboratory for understanding spiral galaxy formation and evolution. The insights we gain from studying Andromeda in detail can be applied to understanding spiral galaxies throughout the universe, even though those distant galaxies can only be studied in much less detail. Additionally, Andromeda and the Milky Way are the only two large spiral galaxies close enough to study in this way. Together, they provide crucial data points for understanding how galaxies like ours form and evolve. Part 11. The Tools of Discovery. How we study Andromeda, ground-based telescopes. Most of what we know about Andromeda comes from observations using ground-based telescopes. These range from modest amateur instruments that can photograph the galaxy's overall structure to massive professional observatories capable of detecting individual stars. The largest ground-based optical telescopes, like the twin 10-meter Keck telescopes in Hawaii, the four 8.2-meter telescopes of the Very Large Telescope in Chile, and the Gran Telescopio Canarias in the Canary Islands, can obtain spectra of individual stars in Andromeda's outer regions. This allows astronomers to measure stellar velocities, chemical compositions, and temperatures for stars too. 5 million light-years away, a remarkable technical achievement. Radio telescopes have mapped Andromeda's neutral hydrogen distribution, magnetic fields, and molecular gas content. The Very Large Array in New Mexico and the Westerbork Synthesis Radio Telescope in the Netherlands have produced detailed radio maps showing the large-scale structure of Andromeda's gas content. Space-based observatories. Space-based telescopes offer advantages over ground-based instruments by avoiding atmospheric distortion and absorption. The Hubble Space Telescope has been particularly productive in Andromeda studies, producing images that resolve individual stars and reveal structures invisible from the ground. The 20 and 15 Hubble image of Andromeda that I mentioned earlier represents the sharpest large composite image ever taken of our nearest galactic neighbour. It contains 1.5 billion pixels and was assembled from 7,198 individual exposures. The image shows a 48,000 light-year-long section of Andromeda, about one-third of the galaxy's visible width, containing over 100 million stars. Other space telescopes have observed Andromeda across different parts of the electromagnetic spectrum. The Spitzer Space Telescope observed in infrared, mapping dust distribution and star-forming regions. The Galaxy Evolution Explorer (GALEX) satellite observed in ultraviolet, tracing populations of hot, young stars. The Chandra X-ray Observatory has catalogued hundreds of X-ray sources, including X-ray binaries and supernova remnants. Each observatory, each wavelength, reveals different aspects of Andromeda's structure and composition. Only by combining observations across the entire electromagnetic spectrum can we build a complete picture of the galaxy. Yes, there were these mysterious spiral nebulae, but most astronomers believed they were within our galaxy. Computer simulations. Understanding Andromeda's structure and evolution requires more than just observations. It also requires sophisticated computer simulations that model how galaxies form and evolve under the influence of gravity. Modern galaxy simulations begin with the initial conditions of the early universe, shortly after the Big Bang, and follow the evolution of dark matter and normal matter forward through cosmic time. These simulations must account for gravity, gas dynamics, star formation, stellar evolution, supernova explosions, black hole growth, and many other physical processes. The computational requirements are enormous. The most detailed simulations can track billions of individual particles representing dark matter, gas and stars as they interact gravitationally over billions of years of simulated time. These simulations require some of the world's most powerful supercomputers and can take months or even years to complete. By comparing simulation results with observations of real galaxies like Andromeda, astronomers can test their understanding of galaxy formation physics. If simulations produce galaxies that look like Andromeda, with similar sizes, masses and structural features, it suggests that the physics included in the simulation is correct. If simulations produce galaxies that look different from what we observe, it indicates that something is missing or incorrect in our models. This interplay between observation and theory, between what we see in the sky and what we can produce in computer simulations, drives progress in understanding galaxies. Citizen science and amateur contributions. Interestingly, professional astronomers don't have a monopoly on advancing Andromeda science. Amateur astronomers have made significant contributions, particularly in discovering novae, stellar explosions that briefly brighten before fading back to obscurity. Novae occur when a white dwarf in a binary system accretes material from a companion star. When enough material builds up on the white dwarf's surface, it undergoes a thermonuclear explosion that brightens the star by tens of thousands of times for a few days or weeks. These events are relatively common in galaxies like Andromeda, with several dozen occurring each year. Professional telescopes generally don't monitor Andromeda continuously, so they miss most novae. But dedicated amateur astronomers who photograph Andromeda regularly can detect these events and alert professionals for follow-up observations. This amateur-professional collaboration has resulted in the discovery and study of hundreds of novae in Andromeda. Additionally, citizen science projects like Galaxy Zoo have enlisted hundreds of thousands of volunteers to classify galaxies, including identifying features in deep images of Andromeda and its satellite galaxies. This crowdsourced approach can find rare or unusual features that automated algorithms might miss. Part 12. Philosophical Reflections. What Andromeda tells us, the principle of mediocrity. One of the profound implications of understanding Andromeda is what it tells us about our place in the universe. Andromeda demonstrates that the Milky Way is not unique or special. It's one large spiral galaxy among billions, with properties that fall well within the normal range for such objects. This realization is an example of what's sometimes called the principle of mediocrity, or the Copernican principle. Throughout history, humans have repeatedly discovered that we're less special than we thought. Earth is not the center of the solar system. The Sun is not the center of the galaxy. The Milky Way is not the only galaxy. Our location in space appears to be entirely typical, with no special properties that distinguish it from billions of other locations. This principle has proven remarkably powerful in science. When cosmologists build models of the universe, they generally assume that the laws of physics work the same everywhere, and that our location is not special. This assumption, backed by observations showing that distant galaxies obey the same physics as nearby ones, has enabled remarkable progress in understanding cosmic history and structure. But the principle of mediocrity raises an interesting question. If our galaxy is typical, and our star is typical, and our location is typical, what about life? If we're typical in every other respect, shouldn't life also be typical? Shouldn't the universe be teeming with life, with countless civilizations arising on planets around other stars? This is the essence of the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody? If life and intelligence are common, why haven't we detected any signs of alien civilizations? Where are the radio signals, the megastructures, the spacecraft?" The Fermi paradox and Andromeda. Looking at Andromeda makes the Fermi paradox even more acute. Here's a galaxy with 1 trillion stars, likely trillions of planets, and billions of years of history. If life arises readily wherever conditions are suitable, Andromeda should be full of life. And if even a tiny fraction of living worlds develop technological civilizations, there should be millions of alien civilizations in Andromeda alone. Some of these civilizations, by simple statistics, should be millions or even billions of years older than ours. What could a civilization accomplish given 1 billion years of technological development? Could they spread throughout their galaxy, colonizing star after star? Could they build structures so massive that we'd be able to detect them across intergalactic distances? Yet when we look at Andromeda, we see no evidence of galaxy-spanning civilizations, no obvious megastructures, no signs of intelligence. The galaxy appears as we'd expect a collection of stars, gas and dust to appear, following the laws of physics, with no indication of deliberate modification or control. This could mean that life is rare, that the transition from non-life to life requires such an unlikely chain of events that it only happens once per galaxy or even less frequently. It could mean that while simple life is common, complex life is rare, or that intelligence is an evolutionary fluke that rarely occurs. It could mean that technological civilizations inevitably destroy themselves or choose to remain hidden. Or it could simply mean that we don't yet know what to look for. Perhaps galaxy-spanning civilizations exist, but don't leave the kind of obvious signatures we'd recognize. Perhaps intelligence takes form so different from our own that we literally can't conceive of them yet. These are deep questions without clear answers, but Andromeda, by its sheer size and age, makes them impossible to ignore. Cosmic loneliness and connection. There's something poignant about Andromeda. It's our nearest large galactic neighbor, close enough that we can study it in detail, see it with the naked eye, watch it slowly approaching for an eventual collision billions of years hence. And yet a gulf of 2.5 million light-years separates us, a distance so vast that light itself takes millions of years to cross it. If there are civilizations in Andromeda, we're completely isolated from them. Even communication at the speed of light would take 2.5 million years each way. A message sent today wouldn't receive a reply for 5 million years. That's longer than our species has existed. This isolation is profound. For practical purposes, we can never have a conversation with anyone in Andromeda. We can't visit, can't trade, can't share cultures or ideas in any meaningful real-time sense. The distance is simply too vast. And yet we're connected by gravity. Andromeda and the Milky Way are gravitationally bound, their dark matter halos already overlapping, their futures inextricably linked. In 4 billion years, they will merge into a single system. Any civilizations in either galaxy will become part of the same merged structure, their fates united even if they never meet or communicate. This cosmic loneliness, mixed with ultimate connection, is one of the strange paradoxes of life in a universe this large. We're isolated by distance, but connected by gravity and shared physical laws. We're separated by time, but united by cosmic evolution. The privilege of understanding. Finally, there's something profound about the simple fact that we can understand Andromeda at all. We're biological organisms that evolved on one planet orbiting one star, and yet we've developed the conceptual tools to understand an object containing 1 trillion stars spread across 220,000 light-years of space. This required thousands of years of intellectual development, the invention of mathematics, the development of physics, the creation of telescopes and cameras, the formulation of quantum mechanics and general relativity, the understanding of nuclear fusion and stellar evolution. Each generation built upon the achievements of previous generations, gradually assembling the conceptual framework needed to comprehend galaxies. And now, just a few centuries after we first built telescopes, we can look at Andromeda and understand what we're seeing. We know its distance, its size, its mass, its composition, its age, its structure, its future. This represents a triumph of human curiosity and intelligence that should not be taken for granted. Every time you look at Andromeda, you're benefiting from the accumulated knowledge of thousands of brilliant people across centuries who each contributed a small piece to our understanding. You're standing on the shoulders of giants, seeing farther than any previous generation could see. Conclusion: bringing it all together. What we've learned. We've covered an enormous amount of ground in our 3-hour journey. Let's take a moment to recap what we've learned about Andromeda's true size. In physical dimensions, Andromeda's visible disk extends approximately 220,000 light-years across, making it one of the largest spiral galaxies in the nearby universe. Its stellar halo extends perhaps 300,000 light-years from the galactic center, and the dark matter halo reaches out possibly 600,000 to 800,000 light-years or more. The galaxy's sphere of gravitational influence extends roughly 1 million light-years from its center, meaning the total gravitational structure of Andromeda spans about 2 million light-years in diameter. In terms of mass, Andromeda contains approximately 1 trillion stars, with a total stellar mass of about 200 to 400 billion solar masses. Including dark matter, the total mass is roughly 1.5 trillion solar masses or more. In angular size on our sky, Andromeda extends about 3 degrees by 1 degree, making it about 6 times the width of the full moon, though its faint surface brightness makes it appear much smaller to the naked eye. In time, the light we see from Andromeda left the galaxy 2.5 million years ago, before our species evolved. And in 4 billion years, Andromeda will merge with the Milky Way to create a new, larger, elliptical galaxy. The ladder of understanding. Throughout this journey, we've built a ladder of understanding, starting from human scales and extending outward to galactic scales. Let me recap that ladder one final time to cement the progression. Earth, 8,000 miles in diameter. Earth's orbit, 93 million miles from the Sun. Neptune's orbit, 2.8 billion miles from the Sun. The Oort cloud, 1.6 light-years from the Sun. Proxima Centauri, 4.24 light-years away. The Milky Way, 100,000 to 180,000 light-years across Andromeda's distance. 2.5 million light-years, Andromeda's diameter. 220,000 light-years, Andromeda's dark matter halo. 600,000 to 800,000 light-years or more, Andromeda's gravitational sphere. 2 million light-years. Each step represents an increase in scale of roughly 10 to 1,000 times. By climbing this ladder patiently, one rung at a time, we've reached a genuine understanding of cosmic scale that would be impossible if we tried to jump directly from everyday experience to galactic dimensions. The night sky will never look the same. If you go outside tonight and find Andromeda in the sky, that faint, fuzzy patch will mean something entirely different to you than it did before our journey. You won't just see a smudge of light. You'll see a trillion suns, a vast wheel of stars and gas and dust spanning distances that light itself takes hundreds of thousands of years to cross. You'll know that the light entering your eyes began its journey before humans existed, that you're seeing the galaxy not as it is now, but as it was in the deep past. You'll understand that this galaxy is rushing toward us, that 4 billion years from now it will collide with our own galaxy in a cosmic dance that will create something entirely new. You'll comprehend that each tiny dot of light in that fuzzy patch is a sun, potentially with planets, possibly even with life. You'll grasp the sheer improbability of being able to see such an object with your naked eyes, photons from 2.5 million light-years away, somehow making their way across the intergalactic void to land on your retina. This is what understanding does. It transforms perception. It turns meaningless patterns of light into windows onto the cosmos. It connects you across billions of years and millions of light years to events and structures that dwarf anything in everyday human experience. The continuing journey. Our journey today has focused on one question: how big is Andromeda really? But answering this question has opened up hundreds of others. What is dark matter? How do galaxies form? Why does Andromeda have the structure it does? Are there civilizations in Andromeda looking back at us? What will the merged galaxy look like billions of years from now? These questions and countless others drive ongoing research into galaxies, cosmology, and fundamental physics. Every year brings new discoveries, new insights, refinements to our understanding of how galaxies work and how the universe evolves. The study of Andromeda specifically continues to yield surprises. Recent observations have revealed previously unknown stellar streams, suggesting additional galaxy mergers in Andromeda's past. New measurements of stellar motions are refining our understanding of the dark matter distribution. Detailed studies of individual star-forming regions are revealing how stars form in environments different from our own Milky Way. Each discovery adds another piece to the puzzle, another small increment to our understanding of this magnificent cosmic structure. A final thought. We began this journey by noting that the human brain didn't evolve to understand galaxies. We evolved for much more mundane tasks, like finding food, avoiding predators, and cooperating with other humans. And yet, somehow, we've stretched our minds to encompass objects 1 trillion times more massive than ourselves, structures that span distances we could never cross, even if we had billions of years to try. This capacity for abstraction, for building mental models of things we can never directly experience, may be humanity's greatest achievement. It's what allows us to do science, to create art, to build civilizations that outlast individual human lives. When you look at Andromeda tonight, you're exercising this uniquely human capacity. You're using your evolved primate brain to comprehend something that exists on a scale inconceivably larger than anything in your direct experience. You're connecting across 2.5 million light-years and billions of years to understand your place in a vast, ancient cosmos. This is the gift that science gives us. Not just knowledge for its own sake, but a genuine expansion of human consciousness, a way of seeing and understanding the universe that enriches our experience of being alive. Andromeda is not just big. It's not just 220,000 light-years across or 2 million light-years away. It's a window onto the cosmos, a reminder of how vast and ancient and magnificent the universe truly is. And the fact that you can understand it, even a little bit, the fact that you can look up at that faint smudge of light and know what you're seeing, that's nothing short of miraculous. So go outside tonight if the sky's clear. Find Andromeda. And take a moment to truly see it, not just as a fuzzy patch of light, but as what it really is. A trillion suns, a vast island universe, our nearest large galactic neighbour rushing toward an appointment with destiny 4 billion years from now. The universe is bigger, older, and more magnificent than everyday experience suggests. And now you know, really know in your bones, just how big one small piece of it truly is. Thank you for taking this journey with me. May you never look at the night sky the same way again.